Last lecture, we defined the frequency response. Substitute S equals j omega in G of S, take magnitude and phase. Today, we'll learn to draw the magnitude curve fast, without plotting 100 points by hand. The trick is the Bode magnitude plot, log frequency on the x-axis, decibels on the y-axis. In this language, the rational transfer function becomes a sum of straight-line asymptotes. We just stack them. Why log frequency and decibels? Two reasons. First, magnitudes span huge ranges, often 6 orders of magnitude. A linear axis cannot display them. The decibel scale, 20 log of the magnitude, compresses everything into a manageable strip. Second, when factors multiply, their decibel values add. 20 log of a product equals the sum of 20 logs. So if we decompose G into factors and know each factor's magnitude in dB, we just add them on the plot. Multiplication becomes addition. Curves become straight lines. That is the entire idea behind the Bode magnitude plot. Step 1. Factor decomposition. Any rational transfer function can be written as a product of simple atoms. Type 1, a constant gain k. Type 2, an integrator 1 over s or a pure differentiator s. Type 3, a simple real pole 1 over s plus a or a simple real zero s plus a. Type 4, a complex conjugate pair, written as a quadratic s squared plus 2 zeta omega n s plus omega n squared in the denominator or numerator. Every transfer function in classical control is a product of these 4 types. Once we know the magnitude rule for each type, and there are only 4, we can sketch any Bode magnitude plot in seconds. Step 2. Magnitude rules per atom. Constant k. Magnitude in decibels is 20 log k, a flat horizontal line. Positive k shifts the whole plot up by 20 log k dB. Integrator 1 over s. Substitute s equals j omega. Magnitude is 1 over omega. In dB, minus 20 log omega. A straight line of slope minus 20 dB per decade, passing through 0 dB at omega equals 1. Differentiator S, plus 20 dB per decade, also through 0 at omega equals 1. Simple pole, 1 over s plus a. Below the corner frequency omega equals a. The magnitude is roughly 1 over a flat asymptote at minus 20 log AdB. Above the corner, the magnitude decays as 1 over omega, slope minus 20 dB per decade. 2 asymptotes that meet at the corner. Simple 0 s plus a, the mirror image. Flat below the corner, plus 20 dB per decade above. Complex conjugate pair. Same idea, but the slope is twice as steep, minus 40 or plus 40 dB per decade, and there is a resonant peak or dip at the corner whose height depends on the damping ratio. 5 rules. Memorize them once, use them forever. The construction recipe. First, write G of S in factored form. Identify all corner frequencies, the points where each factor's asymptote breaks. Second, start at low frequency. Find the magnitude there. Contribution from K plus contribution from integrators or differentiators. Third, walk the frequency axis from low to high. At each corner, change the slope by the contribution of that factor. Minus 20 dB per decade for a pole, plus 20 for a zero, double for complex pairs. Fourth, the sum of all asymptotes is the asymptotic magnitude plot. Worked example. G of S equals tan divided by S times S plus 1 times S plus tan. Factor it. Constant, tan. Integrator, 1 over s. 2 simple poles, 1 over s plus 1 with corner at omega equals 1, and 1 over s plus 10 with corner at omega equals 10. Low frequency contribution. Constant gives 20 log 10, which is 20 dB. Integrator gives minus 20 log omega, a slope of minus 20 dB per decade. Each pole adds minus 20 log of its corner value at low frequency. Minus 20 log 1 is 0, minus 20 log 10 is minus 20 dB. So the low frequency asymptote is 20 minus 0 minus 20, plus the integrator's minus 20 log omega. Net low frequency line, minus 20 log omega, slope minus 20 dB per decade, passing through 0 dB at omega equals 1. Walk through the corners. At omega equals 1, the pole at minus 1 kicks in. Slope changes by minus 20. Total slope becomes minus 40 dB per decade. At omega equals 10, the pole at minus 10 kicks in. Slope changes by another minus 20. Total slope becomes minus 60 dB per decade. And we're done. 3 line segments, minus 20, minus 40, minus 60, meeting at omega equals 1 and omega equals 10. That is the asymptotic magnitude plot for the entire transfer function. How accurate is the asymptotic plot? Very accurate, with one small caveat. The true magnitude curve is smooth. It does not have sharp corners. It deviates from the asymptote by exactly 3 dB at each simple pole or zero corner, minus 3 dB for a pole, plus 3 dB for a zero. Far from any corner, asymptote and true curve agree perfectly. Near a corner, smooth out the kink by 3 dB and you have the actual magnitude. For complex conjugate pairs, the deviation can be much larger, a tall resonant peak when damping is low. We will revisit this when we cover second-order details. Summary. Bode magnitude plot, 20 log magnitude versus log frequency. Factor the transfer function into atoms, constants, integrators, simple poles and zeros, complex pairs. Each atom contributes a piecewise linear asymptote with known slope. Sum the asymptotes, get the magnitude plot in seconds. Smooth corners by 3 dB if you want the exact curve. The same recipe scales to any rational transfer function. Next lecture, phase. Same factoring trick, different rules, same speed. Then we have the full Bode plot, magnitude and phase together. And we can read the system's behavior at every frequency in one glance.